Alright, what's up guys? It's Probability by Pitman, Chapter 2, Review Section, Problem number 18. Okay, so 7 dice are rolled. Write down the unsimplified expressions for the probabilities of each of the following events. A, exactly 3 sixes. So I think this one's pretty simple. It's clearly just a binomial distribution. We have 7 independent Bernoulli trials, of which we have 3 successes, where success is defined as getting a 6. And probably getting a 6, 1/6, because you have 6 total numbers, of which 6 is one of them. Then it's the third power because there are 3 successes. Then 5/6, which is a complement of 1/6, which is defined as a failure, which is getting a non-6 value. That'll be to the fourth power because we have 3 successes, 7 total trials, so therefore there must be 4 failures. Alright, so that's our answer for part B. Now, they're probably getting 3 of one kind and 4 of another, so we can do a binomial distribution once more. I'm going to write it as a multinomial because I find that helps me understand it better. So 7, 3, 4, which is equal to 7 factorial over 3 factorial times 4 factorial, which is equal to 7 choose 3, which is equal to 7 choose 4. So, it's really the same thing as a binomial. I just wrote it out this way because I find it more helpful. Okay, so then probably getting a 3 of one kind to the third power, 4 of another to the fourth power, because each kind has a 1/6 probability. However, we're not done. They don't say like 3 6s and 4 5s, right? They just said 3 of one kind and 4 of another. So that means we have to account for all the different ways you can get this. So I think the best way to go about doing that is multiplying by our rank factor, which will be 6, 1 and 5, 1, because you're picking 1 out of the 6 numbers, and then you're picking 1 out of the 5 numbers. So this first one, let's say, is the one we get 3 of, and the second one is the one we get 4 of. So we're basically showing the number of combinations possible where you're drawing 2 numbers, basically, and then we're multiplying by this probability. So 6 choose 1 is equal to 6, 5 choose 1 is equal to 5, so 30. So there are 30 different ways to get 2 different numbers together. And then if you multiply that, the probability of getting 3 of one kind and 4 of another, then you'll get the probability of that, yeah. Or this isn't the probability of getting 3 of one kind and 4 of another. This is just like a specific instance. So you're multiplying that specific instance by the total number of instances possible, unique instances possible, and that's how you get the probability of 3 of one kind and 4 of another, because you're adding it up however many times this reality can occur. Alright, I hope that made some sense. I'll just say it once again. Basically, we're picking 1 out of the 6, showing the amount of ways we can pick 1 out of the 6 and 1 out of the 5, the number of ways to do that in total. Okay, the explanation might have been a little confusing now that I think of it, but I hope it made some sense. It was kind of jarbling at the beginning, but I think the end was okay. Alright, sorry about that. Part C. 2 4s, 2 5s, and 3 6s. Okay, this one's a clear case where a binomial is just ridiculously easy. Just do 7 and then 2, 2, 3. So once again, that's just 7 factorial over 2 factorial times 2 factorial times 3 factorial. Pretty easy. Then just do the probability of each, so 4, 5, and 6. Okay, so probability of getting a 4 is 1/6 to the second power since you get 2 of them. 1/6 to the second power since you get 2 5s, and then 1/6 to the third power since you get 3 6s. Yep, pretty easy, I think. Alright, so probability that each number appears. So for each number to appear, when you have 6 total numbers and 7 total rolls, is 1, or the number of possible combinations is 1, 1, 1, 1, 2, 3, 4, 5, 2. Okay, yeah. Because you have to realize that when you have 6 total numbers and 7 total rolls, that means that 5 of the numbers will appear once, and the last number, the 6th number, will appear twice. There's no way around this. This is the only way this can happen. Once you come to that realization, it's a pretty simple multinomial distribution. So 1/6 to the 1 power, 1/6 to the 1 power, so 1/6 power, and then 1/6 to the second power for that number that appears twice. But we're not done here. You have to think about how many possible ways there are to arrange this. You could have, like, let's say let's write like what each of these numbers represents. You could write 1, 2, 3, 4, 5, 6. So there are 1, 2, 5 all have one of them, but then 6 occurs twice. Or you could write like 2, 3, 4, 5, 6, 1. So that means 2, 3, 4, 5, and 6 occur once, but then 1 appears twice, right? And you can do this so many different ways. We have to account for that. So it's actually a lot easier than you would think, because just think about how many ways you can arrange it. Since all the ones are the same, it really doesn't matter where they are. The only thing that matters is where the 2 is. The 2 can be in 6 different spots, since there's 1 here, 1 here, 1 here, 1 here, 1 here, and 1 here. So the way I like to think of it is just picking the slot where the 6 appears. So there are 6 slots, of which we want one of them for the 2 to go into. So we do 6 choose 1. Another way to think of it is just the number of possible ways to arrange this. Once again, you could have like 1, 1, 1, 1, 2, 1, 1, 1, 1, 2, 1. And if you do all possible combinations of this, you'll get 6 total of them, which is equal to 6 choose 1, which is equal to 6. So let's just simplify this down a little. So I'll leave it as 6 choose 1, which is equal to 6, because I think that helps with like bookkeeping and just understanding what's going on. I'll leave the multinomial as well. You can still simplify this pretty easily, but I think it's good for bookkeeping. But then the 1, 6, it's honestly fine. Let's just simplify that. And boom, that, oops. Alright, I wrote the answer kind of messily, but that is our answer. Alright, part E. Okay, this one's a little, if you think about it, if you calculate this manually, doing a sum of 9 or more when you roll 7 dice is ridiculous. That would take way too long. So an easier way is to do 1 minus probability of sum 8 or less, which is pretty easy because you realize that when you're rolling 7 die, the smallest possible sum is 7, because you can roll a 1 7 times. So really what we're doing is p of sum 7 and p of sum 8. From here, I think it's pretty easy. So probability of sum 7 just means you're rolling a 7 or a 1 7 times. So we can do a binomial where it's 7 choose 7, because 7 independent Bernoulli trials, of which there are 7 successes, where a success is defined as getting a 1. Yeah, and then there's our P of 7. P of 8, it's really the same thing, or it's a very similar thing, because probably getting 8 is just, the only way to do that when you're rolling a die 7 times is getting 6 ones, and then a 2. That's really the only way you can do that. So, once again, it's just a simple binomial. We'll define a success as getting a 1. So there are 7 independent Bernoulli trials, of which there are 6 successes. And then a success has probability 1 6, and it'll be to the 6th power. And it'll be 1 6. And then there's one failure where you roll a 2. And that will be to the 1th power, because it can only occur in one way. Let's actually write it as a multinomial, because I think that's just better to understand. So probability of getting a 7, probability of getting sum 8 is just getting 6 ones and 1 2. So 6 ones and then 1 2. Okay. I really shouldn't have written that. That's okay, there we go. Okay, there we go. And then times 1 6 to the 6, where we have 6 ones and then 1 2. Alright. I kind of jumbled that explanation, but I think it still makes some sense, hopefully. Alright, I hope this video was some help, and thanks for watching.